So yeah, our exam's on Friday. And I just went to ProctorU before class right now, and there's still like 5 or 6 people that have not signed up for ProctorU. So, and I think it's like 3 or 4 of you from this class. So just FYI, you already passed the deadline. So you're going to have to pay now. And that's not an excuse. So if you took ProctorU exam 1, you got to take ProctorU exam 2 and all our other exams. And you've already passed the deadline. It's already free. So they're not going to like, you know, give you any like, oh, okay, we'll let you slide this time. I don't understand why you guys don't, you know, do it. Like, why don't you just make the appointments all together? Like, you know, the dates of the freaking exams from like till the end of our semester. Just do them all. I don't get it. But too bad, so sad for you. I don't know how much they're going to charge you. What else? I think that's it. Does anybody have any questions or anything like that before I start? So obviously today I'm lecturing again about acid-base titrations. So we're done with redox. Does anybody have any questions on redox? Are you guys kind of comfortable with it? Kind of. Okay, so I mean, you notice that it's the same. You gotta just know the states, and if you know the steps, you should be fine. Do it exactly like we did in class. Is it balanced? Okay, find the oxidation states. If something's changing, find out who's Leo, who's Ger, and then the hardest part is putting those oxidation half reactions together in the correct form. But I mean, it's really it. That's it. So, and you got to be able to know the 7 different types of redox reaction. So if I give you a reaction, you got to say, okay, no, yeah, that's a combustion, or no, that's a disproportionation. So you got to be able to do that. Okay. Questions?
Dr. T?
Yes.
Yeah. When we were in tutoring Monday, Jalen was telling us to reduce the reactions, but we were like saying you never said anything about that. So he didn't really know. He said reduce them, but I just want to know.
No. He's talking about redox reactions with metals, and like those are more complex redox reactions. Yeah, that you either have to reduce it by adding waters or oxidize it by adding H pluses. You don't do that. You don't do that here.
No, he was telling us to simplify our final answer.
Like if you had 2 all the way across, I mean, like if you had something that can be simplified by 2 all the way across or something like that.
Well, that's always, I mean, if that's what you're talking about, then that should have been done when you first balance it. You should always have the reduced version when you balance it. Okay, so don't freak out. Like, you know, when you first, before you even start the redox problem, you balance it, right? And if, let's say you get 6, well, I don't want to use 6, that sounds like a bad number, but like 8, right? Then obviously you can reduce everybody by dividing by 4. But that doesn't happen at the end, that happens at the beginning. And that's every time you balance any reaction. You should have the lowest common, is that multiple? Is that what it's called? The lowest common, you know, of everybody. If you can, then do it. It's not wrong. So I mean, I do want to, like, I wouldn't mark you off for it, but it just, that's the convention. You would use the lowest multiples of everybody. Does that make sense?
Yes, ma'am. Thank you.
Yeah, you're welcome. I thought he was doing something else with adding waters and adding H pluses. I'm like, no, you're not supposed to do that. You don't do that in this class. Any other questions? Okay. So let's do our quiz. What else? I told you about ProctorU. I'm not missing anything, right? Yeah, and tomorrow we're having class, but we might have some guests from section 2 because I'm not having section 2. And I think that's it. Okay, let's share my screen. Let's do our quiz. And funny enough, oddly enough, that you mentioned about lowest common whatever of a reaction, look what your quiz is today. So I want you to balance the reaction. Today is balancing. So balance the following reaction. So what I want you to do is I want you to place the numbers, just the numbers that are supposed to go in front of all of these guys. So even if it's a 1, put a 1. You know what I mean? So it could be a number, space in your answer. Do you understand? Hello,
Yes,
everybody?
ma'am.
Okay. So place your number separated by a space. So you should have 3 numbers. All right. I don't know.
It's gonna go in order.
Yes,
of
of
the
course it goes in order. Yes, of course. Of course it goes in order. On the board right now or on the screen, does anybody know or can tell me in their own words what a titration is and why do we use it? What's the most common, why is it, yeah, why are titration, what are titrations most commonly used for?
Neutralization.
Say it again, Ariel.
Neutralization.
Okay.
Of the acid in the base.
Okay, that's exactly right. So quantitatively studying acid and bases solutions are usually done with this experiment called a titration. So can you kind of explain what a titration is in your own words besides using these fancy solution of accurately known concentration?
It's like combining acid and a base together to get water and something else.
Salt.
So
You
that
get the
is,
salt, right?
yeah, so that is the reaction that's happening behind the scenes, right?
Mhm.
But the titration is the actual experiment on how, and then you get the, you know, you get the results from this experiment, and then what happens behind the scene is exactly what you said. So a titration, just to kind of, before we start, is exactly what Ariel said. When you have many different types of titrations, but the only type of titration that you guys are responsible for, Terion, do you have a question?
yes.
I thought you were doing this, like hand up. Anyway, the only type of titrations that you guys have to worry about are strong acid and strong base, right? So if I take a strong acid and I react it with a strong base, it's great because there's not that many options, right? There's not that many strong acids and not that many strong bases. So it's not like you have to do anything really new here. So whenever you do that, whenever you react a strong acid and a strong base together, they neutralize, which is why, like Ariel said, is called a neutralization reaction. So when that happens, you always get the same products, always, which is why these type of reactions are really easy. So whenever you do a strong base and a strong acid together, you always get what and what? Does anybody know? What?
The water and the salt.
Right, you get salt and water, okay?
I have a question.
Yes.
How do you know if it's like a strong base based off of the chemical formula or like a strong acid?
The only ones that you know that have been exposed, that you have been exposed to, are strong acids. I mean, sorry,
Okay.
strong bases. So barium, sodium, what's the other one? Potassium hydroxide, barium hydroxide. There's only like three or four. And it's not that those are the only strong ones. It's just comparatively, those are usually the stronger ones. And those are the ones that you've only been really exposed to in your book, right? It has like a chart with like 3 or 4. So that's all you really got to know. And then the strong acids is really the ones that we've been talking about: hydrochloric acid, phosphoric acid, I don't know what other ones, but you know, the ones that you've been exposed to. So you don't have to go anywhere else other than that, right? Like you don't have to go research deeper. Because we could go more complex. I could tell you, no, you got to know all this and that, but that's not what the point is. The point is for you to understand what the experiment is and what you're supposed to be seeing as far as the reaction. So once again, strong acid, strong base, when you react those things together, you always get salt and water. We're going to do the actual reaction so you guys can see. But first, I want to talk about the actual experiment. So if you were in, let me just put everything. So if you were in lab, sorry, did you have a question, Chloe?
No, carry on did.
Oh, sorry. Go ahead.
It's very blurry right now, like, because it was a while ago, but like our old chemistry teacher, he had us like, there was some solution and like we were trying to like, we were putting another solution in there to like try to get it like just pink. And if it was too much, it would turn like completely like solid pink, or like not
Yep.
solid pink, but really
Yep.
pink. Is that basically what this is?
That's exactly what this is. Look at the board. Look at the pink.
Oh, I
Yeah,
see.
so that's exactly what it is. That's exactly what it is. So it's a very simple experiment. So, but what happens is you would have, and I don't know if, let me use my pen, but you would have this Erlenmeyer flask, right? And in this flask is the thing that you don't know about, right? It's the unknown. It's the dude that you're trying to figure out, right? And then this apparatus here that you can only really see a little bit is called the burette. And a burette is really, really long, skinny, and it's got a bunch of like graduations. You know what I mean? Like a bunch of numbers really close together. So it's really precise. It's a really precise glassware that you would use. In that, you would put the solution that you know everything about. You know its concentration, you know how much you're pouring in because you pour it in. And you use that's in the burette to drop into the unknown solution until that unknown solution turns color. And the moment that, and it's supposed to, I mean, this, I would say, I would argue that that's already too pink. But like he was saying, the moment that it turns pink or it changes color is the moment that you stop, right? Because you have this little thing here that you open it or you close it. As soon as it starts turning pink, you stop. And then that's when you do your calculations. That's when you say, okay, I used this much of the thing that I know all about to turn this unknown a color. So that all turns into, like, think about it. I mean, we've been doing problems before. That all turns into molarity, milliliters, and you know the reaction that's happening, right? So I know that I have this unknown. I don't know what the concentration is, but I know who it is. And I know I've added this many milliliters and this concentration of this known solution. So with that information in the background, you can actually do a bunch of calculations. So that's the experiment, right? This is called the titration. Now there's like a couple things that you do need to know, just logistics about what a titration is. But again, the thing that's in the burette, you know everything about. You know its concentration, you know who it is, right? The identity of it, and you know how much you put in because of what you're doing in the experiment. This guy here in the Erlenmeyer flask, that's the unknown. So you know who it is, but you don't know the concentration, which is what you're trying to find out. So you would have this little thing, which is called an indicator. Okay, so actually I didn't even realize it's on the board. Indicator, and it's the subject it's the thing that turns color the moment, because look what's happening, right? Let's say you have a base here, right? And here's your acid, right? So obviously you would put a bunch of drops of this indicator in this unknown acid before you do anything else. Just one or two drops, that's all it needs. 1 or 2 drops, you would put it in here and it stays clear, right? Before you even start the experiment, that solution stays clear just like you see it on the board. It's still clear. The moment that solution turns pink, that tells you, for us, the people who are doing the experiment, that it has turned, it's not an acidic solution anymore, because you've been adding base. That's what you're doing. You're adding base drop by drop by drop. That moment that it turns over to the basic side is when it turns color. So that's how you know when to stop. And that tells you how many milliliters of that unknown base, of that base you have added to this unknown acid. So you call that the indicator. That's what you use before you even start the experiment. You put like 1 or 2 drops and then you start pouring the base in, right? Okay, what is this? This is equivalence. What does it sound like, right? It's the point when they're equal. Remember, this is all moles. If you go back, like, this is all moles. How many moles of acid do I need to add to this moles of base to make them neutralize? That's the whole point of a titration, is to make them neutral. Just to kind of take a step back, and I think I've said this before in class, but take a step back for a second. Forget about this experiment. If I was in lab and I was working with an acid, right, and I spilled it on me, which is bad, right? It spilled it on me. I theoretically, in theory, I could go and take a base and pour it on me as well, which also, by the way, bases are dangerous too. But in theory, I spilled acid. I can go and say, oh, let me just go ahead and take some base and pour that on me, and then I would be okay. Okay, so the whole point of a neutralization reaction is you have a base to make it not dangerous anymore. You would add exactly the correct amount of base to neutralize it so that it becomes water. That's what's happening. And like she said, you know, Ariel said, you get a salt and a water. Salt doesn't hurt you and water doesn't hurt you. So that is basically what you're doing in this reaction, just very controlled. Okay, and please don't do that. Just have to disclaimer that, do not do that, because for that to work, you need exactly the correct amount of base with exactly the correct amount of concentration. So don't do that. But in theory, that is what you're doing. You're neutralizing the other thing by creating salt and water. So anyway, equivalence point means the exact point when the moles of the base and the moles of the acid are equal. That's the moment that that thing turns pink. That's exactly the moment when it turns pink. So that's what equivalence point is. The equivalence point is when you stop the reaction, because that means that that's it. You've already added enough moles of what's in the burette to make, to suck up all of the H+ ions from the acid, okay? What is, now there's another thing called endpoint, which is not on this slide, don't know why, but can anybody tell me what endpoint is? There's an equivalence point, which means they're equal, right? That kind of helps you remember.
Is that,
What's the endpoint?
is it, this is a guess. Is it, if like once you've passed the equivalence point and you've changed it, not from like neutral or equal, but all the way into the other, like if you had a base and you added an acid until it was completely an acid, or had a acid and added a base until it was completely a base?
That's a good guess, but that's not right, but that's a good guess. So endpoint is, we're human and we make mistakes. So equivalence point is mathematically, like I said, when they're exactly equal, right? But what are you counting on? This whole experiment is based off of, you're stopping this experiment based off of what?
Your vision.
Exactly. And everyone's vision is not very good. So that's what Terion was saying. Like, usually when you do this experiment, you have like a piece of like a white paper, something very bright, and you like stand it in front, or in the back of the Erlenmeyer flask, so it can help you visualize the change in color, right? Because and I'm serious, like this is the experiment the students hate the most, because they overshoot it. And if you overshoot, and overshoot means by one drop. I mean, that's how important it is for you to do this very, very slowly, right? Because if you do it, then that little light pink, and like I said, I think that's already too pink. But if you maybe put one more drop, that thing will turn fluorescent pink, and you're done. You're done. Forget it. You got to start all over again, which is what happens to every student every single time when you do it the first time. So you can go fast, but you have to slow down when you start seeing that the thing is, oh wait, what happens is you'll go fast and you'll drop a bunch of base and it won't even change color. Like you don't see anything happening, but then all of a sudden you'll keep dropping, and then you'll see pink, and then it goes away. Pink, and then it goes away. That's the moment when you need to start going really slow, because it's close. It's really close, and you're gonna overshoot it, and then you're gonna hate your life. But anyway, so endpoint. Endpoint is the moment that you stop because of your eyes. So there's a what's the word? There's a what's the word I'm looking for? There's an error there, right? But between the equivalence point, which is the point that you're really supposed to stop, and the endpoint is when your eyes can see to stop. There's a range there, right? So that's your error, basically your human error. But that is the endpoint. The endpoint is when you stop, when you see the color, and your eyes might not be as good as somebody else's eyes. So that's it. Any questions on just the process? Because now we're going to actually look at the reaction and talk about problems. No? Anybody? Okay. So it is pretty easy. I mean, this is a really easy compared to redox and all this other stuff. This is really easy. This is not a redox reaction for the reason that no oxidation states are changing. Nothing is changing. Just like a precipitation reaction is not a redox, right? This is also not a redox. Okay, so, oh, there we go. So titrations can be used in the quantitative analysis of acid-base titrations. Realize that there's, like I said at the beginning, there's a bunch of different titrations. You don't have to have strong acid, strong base. You can have strong acid, weak base, strong acid, right? But you don't need to do all that. That's quantitative analysis, and we do that there. And these are very, very simple titrations because you only have 3 little sections. And if you think about it, the section number 1 is nothing has started. So you have all acid in your Erlenmeyer flask. Section 2 is the equivalence point when everything is supposed to be equal. And then section 3 is when you've surpassed it. So you really only have 3 things that you need to know about as a titration. But that's not in the real world, like strong base, strong weak acid titrations, they have like 5 or 6 different sections, like spots. So there's a bit of more information you would need to know. But anyway, okay. So you have sulfuric acid reacting with sodium hydroxide to yield salt, right? So basically, if you think about it, it's kind of like they switch partners as well, right? So this guy goes with this guy. That's sort of a switch, right? And then you make your salt. And then what's left, the H and the OH make water, okay? So that is always the products. Those are always the products of an acid-base titration, salt and water. So you should have no problem figuring this out. So if you see something like this, first you balance it. I believe this is balanced because this is the first one. You balance it, and then try doing, like, when we did precipitation reactions, we did the molecular equation, which is this equation. And then what was the next equation? What was the second equation called? Like when we broke everybody up, what was that called?
Ionic equation?
Ionic, yes. So let's try to do that. Let's try to do what we did with the precipitation reaction. Let's try to do it with this equation. So if I broke the first one, first of all, let me do this so this is easier for you. Yeah. This is L, which we've never used before. This is L. What does L stand for?
Liquid.
That's right. It's liquid. So break this up for me.
There's 2H plus 1.
Okay.
And there's 1 SO4 minus 2.
Okay.
And then there's 2.
Oh God. Okay. Yeah.
There's 2 sodiums plus 1 with a plus 1 charge.
Mm-hmm.
And then there's 1 hydroxide. No, there's 2 hydroxides with there's 2 hydroxides with a negative 1 charge.
Okay.
And then on the right side, there are 4 hydrogens with a plus 1.
You treat this like a solid. You don't break up water and water.
Oh, okay.
Water. So you would do this because it's just like a solid. I mean, it's not a solid, but you don't, liquid signifies that that's it. I mean, water is water. So that's it. And then you would do the same thing for this. This would be 2Na plus, right? And then what's this one? Same thing. So
Sulfate.
Yep.
2 minus.
Okay, cancel. Cancel what you can cancel. What can you cancel?
The sulfate and the sodium.
So what's left, everybody?
The water.
That's right. So a titration reaction, the only thing that's reacting is water. That's why, in theory, if I spill acid on me, I can freaking pour some base on me and it will be great because all I'm doing is making water. And then that's not harmful to me, right? That's the whole point. If you do this little precipitation action thing that we used to do with the precipitation reactions, you'll see that everything cancels except water, because that's really the only thing that's reacting here. So that is how, oh, I guess that's all I have. But that is the purpose of a titration reaction, is for you to mix acid and base to get salt and water. That's it. So basically you are producing water. Do you have any questions? Because now we're going to do some problems. Think about, okay, so I know now we have to tie in the two slides together. First slide was what a titration experiment is. Next slide is like, okay, let's look at the reaction. But now I can tell you experiment stuff and you have to apply it to doing a problem. So that's what this is, that's what you got to do now. So any questions on any of this before we start? No. Okay, so just same, acid plus base equals salt and water. This is exactly what we just did, right? So hydrochloric acid with potassium hydroxide, you have your salt and water, potassium chloride as the product plus water, and then you break everybody up. And then what cancels is everything but the water. That's exactly what we did. Okay, some problems. Here we go. Oh, okay. Okay, before you, the first things to do is obviously, maybe I can, well, I don't want to show you. Okay, is do, when you read this, you got to, number one, you got to recognize that it's talking about a titration. And there are some keywords. What in the first column, what do you see could be a keyword?
Neutralize.
That's right, right there. And another thing is that you should be able to recognize this. That's a strong acid. This is a strong base. Strong acid, strong base gets you a neutralization, which is an acid-base titration. This is basically like a titration problem. So it's asking how many milliliters of a 1.28 molar sulfuric acid solution are needed to neutralize 60 mils of a 0.427 molar potassium hydroxide solution. That seems like a lot of freaking words and a lot of numbers. So the first thing is, number one, realize it's a titration. Okay, great. So that means that you need to put a reaction. You need to put it down. Like, I want to stress that. I see that a lot sometimes. Like, people just start going into the actual numbers. Don't do that. You can't do that without having a reaction. Why do you need a reaction? Why do you think I'm so insistent on you putting down a reaction? Can anybody kind of tell me?
It'll help you
For
like
molar ratios. Oh,
visualize where those numbers need to go instead of just putting numbers there.
Well, that's number one for sure, to get your mind right, to get it all organized. But also, what I think Ariel maybe said it is, you have to do a reaction because you need to know the molar ratios of everybody. You got to balance it, and you need to understand, because you're going to be, it's like stoichiometry. Remember how we balance it, and then I would tell you, okay, I start with this much reactant. Can you tell me how much product? You needed to balance the reaction to know what the molar ratios were, so that you can use it in the problem. This is the same. You can't answer this without knowing, oh, is it 2 moles or is it 3 moles in this reaction? You can't do it. So please do not. Every problem you do, you guys are good enough now that you can start doing reactions. So do reactions every time you can, because you're going to probably need it. So anyway, yes. So let's do a reaction. This is sulfuric acid. So we would do sulfuric acid plus KOH. Can anybody tell me what the products are?
K2SO4.
Perfect. Plus?
Water, sorry.
Okay, plus water. Okay. Next step is what?
Using the starting values they gave us to get some information.
Nope.
you gotta balance the equation.
Balance. Yes. Wait, I heard someone. Okay. Yeah, yes, you got to balance. So balance it for me, guys.
There needs to be a 2 in front of the KOH.
Okay. Is that it? 2K, SO4, 2H. Yeah, that's it. I think that's it. Right? No. No, it's not. This is it. Then 2 waters, right? Because there's 4 H's, 4 H's. Yeah. So I know that this was like, I hope you understand this little step is crucial, because the fact that now it's not, everybody's not one-to-one here, right? Now you've got a 2 there. That means that if you use that portion of the reaction and you don't put the correct molar ratio, you're not going to get the right answer. So you have to make a reaction. You have to balance it so that you do the problem correctly. Okay, so now we can actually get our mind right, like Terion said, organize everything and see what the hell are they asking. So they want to know how many milliliters of this guy, right? So how many milliliters, and they give you information of that dude. They say that the concentration is 1.28 molar. So, but I want to know how many milliliters of that 1.28 molar is needed to neutralize 60.2 milliliters. So 60.2 milliliters of a 0.427 molar KOH solution. Let me ask you something conceptually. Which one of these, sulfuric acid or potassium hydroxide, is in the burette?
Is in the what?
It's the acid. The acid's in the burette,
Oh,
right?
So
No.
explain to me why you think that.
Because it says how many millimeters of this is needed to neutralize the base, but it's saying how much do you need to add to neutralize, and it's telling you like that's what you're adding in. Like it's asking for how much you need, so that has to be what you're putting into the.
Okay, good. So I just want to ask you stuff like that because in the background, you've got to know, you know, I don't just want you to do problems. I want you to be able to like reason with yourself that you understand what's going on, right? So it doesn't have to be, usually usually actually it's the base that's in the burette for whatever reason, I don't know. But in this case, it's opposite. So good. Now let's start. How do we do this? How do we get this answer? They're asking for volume, right? So they give you the molarity of the sulfuric acid, but they want the volume. How much volume is needed to neutralize 60.2 mils of a 0.427 molar, blah, blah, blah. So where do I start? This should be easy answer. Where would you start with potassium hydroxide or with sulfuric acid?
Potassium hydroxide,
Why?
because we know everything about it.
Yeah, because you have more information about it. So start with the dude that you know everything about. Okay, so you have a reaction. Think back to stoichiometry. Think back, right? So it's the same process. So what do you guys think I should do? Where should I get to? What's like the thing that my goal is to get to so that it can help me?
The K2SO4.
No, you're not going to a product. So, okay, maybe that was the wrong question to ask. So it's not the product. I need to, the question is asking about something about the other reactant, right? So I need to go to the other reactant, but before I do that, I have to get to what unit?
Milliliters?
No, what's New York City? What can get you
moles?
Moles, right? So that was kind of what I was trying to refer to. Like when we used to do these problems before, when we did stoichiometry, the first thing we did is always go to moles. They would give you grams and you would use the molar mass to go to moles because moles is the dude that lets you go across a reaction anywhere. But that's what I mean. Like you have to use the information they give you about potassium hydroxide and get to moles of potassium hydroxide. Once I do that, then I can go wherever they want me to. If they wanted something about K2SO4, then I would go there. But they're not asking me about K2SO4. They're asking me about sulfuric acid, H2SO4. So how can I get to moles with the information they gave me?
They give you molarity.
Okay.
So you can rewrite that as well, if you're starting with the potassium hydroxide, then you could write the molarity as 0.427 moles over 1 liter.
Okay.
But they're telling you that you have, you just divide by the They're telling you that you have 60.2 milliliters, so you can use that to cancel the liters off at the bottom using dimensional analysis to get just moles.
So what's the number I put on top of the fraction, on the other fraction?
You put liters on top and milliliters on the bottom.
Okay, but how about just doing it in one step? I mean, like you can just convert this, right, to 0.0602 liters. You don't have to. So 0.0602 liters. Oh, does that look like a 2? Yeah, 2. Now I can cancel the liters, right? Now I'm in moles of who? Oh, and I forgot, correct unit.
Potassium hydroxide.
Okay, so what do I need to do? I need to go to somewhere else.
Convert it to the sulfuric acid.
So what goes down, and for those of you that are getting nervous, you don't have to put anything down here in this fraction. Just put a 1 if it makes you nervous. But we can just keep going. So what's the unit on the bottom of that last fraction that I need to put?
Moles, the moles of, well, they give you molarity, so you have to put 1.28 moles, and then.
No, stop. What unit do you currently have right now in that problem?
Moles.
Moles of who?
Potassium hydroxide.
Okay, so who needs to go, what unit needs to go on the bottom of that last fraction?
Moles of potassium hydroxide.
Okay, so where would I get that answer?
The equation.
Okay, so tell me what to write as far as the number.
2 moles of potassium hydroxide and then 1 mole of sulfuric acid on the top.
Okay, and why'd you put 1?
Because we need to move to the other reactant to find out how many milliliters we need. So we have to use a mole to mole ratio.
Perfect. So now, for those of you that are keeping score, this cancels. What unit am I in right now?
Moles of sulfuric acid.
Okay, what did they ask us for?
Milliliters of sulfuric acid needed.
Right, and what's the only thing I didn't use? The only information or number that I haven't used yet?
The concentration of the sulfuric acid.
Okay, so concentration are units of?
Molarity.
Moles over liters. So if I use the only thing that's left, I would put this number here, right? The 1.28 molar. I would put, well, if I put 1.28 moles of sulfuric acid, and look what happens, that unit cancels. Look, like magic. 1.28 moles of sulfuric acid over liters of sulfuric acid, then I literally have the answer, because the liters is volume. I would just have to convert that then to, as a final step, to milliliters of the sulfuric acid. So this is how you would do this problem. Can somebody actually give me an answer? What is this? 0.427 times 0.0602 divided by those two numbers at the bottom.
I got 0.010.
0.010 liters of squids.
Of H2SO4.
Okay. So that's in liters, right? So we would just convert it 1, 2, 3. So that means you have 10 milliliters of H2SO4. I know that's really low down there, but that's all it is. I just shifted over the decimal place. So I need 10 mils of H2SO4 to neutralize 60 mils of a 0.427 molar solution. Do you kind of see why I shouldn't be like my little example about throwing base on me and then throwing acid on me? You can't just do that, because you need to have exactly the correct amount to neutralize it. If you don't, then you're still going to die. So don't do that in class. Don't do that in lab. But so do you guys bombard me with your questions, or do you understand? Because this is, I mean, if you think about it, it's the same thing we've been doing from stoichiometry. You're using the equation to help you get to a product or another reactant or whatever. It's the same thing. You just use the information that they give you. And in this case, they're going to give you molarity and volume.
and they're going to ask you, can you tell me what the molarity is of something else, or how much volume of that something else? And you can do it by using stoichiometry. It's really easy. It's really, really easy. But that doesn't mean you don't have any questions. So, do you have any questions?
I do. Yeah, that's a question, but it's these examples are obviously like in the back of the chapter.
Yeah, of course.
Okay.
Yeah. that was Jashawn, right?
Yeah.
Yep. So you should know that answer to that question, Jashawn, because you've been practicing your questions, right? Like from the back of the chapter. Every chapter, you should be doing all the questions in the chapter and in the back of the chapter. So you really just wanted to ask that for the benefit of your teammates, because you know that, right? Mm-hmm.
Yes, I
Throwing some shade. Okay, good. Okay, so yes, go ahead.
Would there be any way, I don't know if you're going to go through the other two today, but I was just going to say, would there be any way we could try them and then come back and go over them at the beginning of class?
So I was going to go over them right now. I mean,
we can do that.
Time? What time is it?
No, I was just asking.
Oh, yeah, no, I want to do them. So let's do any other questions? Okay, so I want to do the second one. Maybe we won't have time to do, I don't know, what time is it? I don't have my watch. I don't have my phone with me. I don't know what the hell's going on. Anybody tell me the time?
11:50.
Oh, yeah, okay, so we probably won't be able to do the last one, which is the last one is the one that I like, because it's conceptual. But we can, whatever, we'll see how far we get. Okay, so second question, what volume, same, if you notice, what volume of a 0.3428 molar, what is that called?
Hydrochloric acid.
Hydrochloric acid solution is required to completely neutralize, ding, 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 ding. That's a keyword, titration, yay. To neutralize 23.55 mils of a 0.2350 molar, what is that called?
Aqueous. Oh,
What did you say?
Is it barium hydroxide?
Yeah, hydroxate?
Hydroxide.
Okay. Yes, so it's barium hydroxide. So somebody, how about Jashawn? Can you tell me what's the first thing I should do?
First, you're supposed to create an equation.
Okay, so help me do that.
Okay, so on the left, which is your reactant side, you write hydrochloric acid and then the aqueous symbol.
The who symbol, AQ symbol, is that what you said? I don't know what you said.
Yeah, aqueous, yeah.
Oh, aqueous symbol, got you.
And then plus your barium hydroxide, aqueous symbol.
Okay, you're not done. That's not a reaction. Come on, Jashawn.
I didn't know. It's coming in late for me. I didn't know if you were like typing or like didn't hear me. But okay. So then on the product side, so on the product side, it will combine the it will be water and then plus barium chloride.
Okay, can you tell me the formula for barium chloride?
It will be, the chloride has a -1 charge in barium. Positive. I think positive 1 charge. So I think it'd just be BaCl.
That's wrong.
Okay.
It would be BaCl2. So I hope you realize that's it right there.
Barium has a +2 charge.
Right.
Okay.
So just good job, Jashawn. But I hope everyone else realizes that is where you can screw up. Nomenclature will kill you every single time. You have to know how to do your compounds, because if not, you're not going to balance it correctly. And if you don't balance it correctly, then you're not going to get the right molar ratio. If you don't get the right molar ratio, then you don't get the right answer. So you have to know your balancing, I mean, your nomenclature. Just like if I tell you barium hydroxide in words, are you gonna know that it would be Ba parentheses OH2? I guarantee you people are not gonna know that. And that's your fault. Your fault, not mine. Because I told you from day one, you need to know nomenclature. Okay, so I hope you realize everything else should be easy. It's this stupid nomenclature that you have to know. Okay, so after that, then you start figuring out what the hell do I want? They want to know what volume of this HCl. So they want to know the same thing, milliliters of this guy. And they give me information. They give me the molarity of this guy, and then they give me a bunch of information. Yes.
It's not balanced, right?
Oh, good job. It is not balanced. There you go. See, I would have gotten it wrong. So can you balance it for me?
I was struggling. I tried to do it, but when I changed one thing, the other thing got changed. But on the left side, I know that there is 4 hydrogen and 2 oxygen and 1 Ba, 1 Cl. But on the right, there's 2 hydrogen and 1 oxygen and 1 Ba and 2 Cl. So you should probably start by putting a 2 in front of the HCl.
Did that.
Oh, well.
And now it's balanced.
It is?
Yeah.
Oh, my math must have been wrong.
Yeah, it's okay. But yeah, so that's a good point to bring up. This balancing of these, remember, my thing is not for you to get stuck 30 minutes on balancing. Okay. So yeah, if you have a bit of an issue with it, stop, erase, and start over, because it should be super simple. Because I don't care that you know how to, I mean, I do care, but that's not important. What's important is, do you know how to do the problem? So
Okay.
yeah, so that it's balanced now. So they want to know milliliters of that guy, and then they give me a bunch of information of the other guy. Can somebody else tell me what do I do next? There's freaking 16 or 15 of you. Can somebody else talk, please?
Can I go again?
Sure. If nobody else wants to freaking volunteer, go ahead.
Okay. Well, first I would do is make sure to convert, because since molarity is moles over liter, I'll convert milliliters into liters.
Okay, do that for me.
So then,
In your head.
so for barium, come again?
Can you do that in your head? Just tell me how many liters this would be.
Oh. That'll be 0.02355
Exactly. Okay, so now,
liters.
yep, okay, so now what do I do?
Okay, well, you'll start off with the stuff that is already given. So then, I guess somewhere you'll write the 0.2350 molar. Am I saying that molarity? Is it molarity or molar?
Well, it's both, but you're using it in a sentence, so it's 0.2350 molar barium hydroxide.
Okay. Okay, yeah. Which
Okay.
is moles over liter.
Okay.
Yeah, barium hydroxide. And then times
Come on, guys.
0.02355 liters over 1.
Thank you, thank you. Okay, so now what unit are we in right now?
Moles of barium hydroxide.
Good job. Right, so now what do I do, Jashawn?
You can use the multimole ratio.
Okay, so tell me what it is.
So on top, you put 2 moles of hydrochloric acid, and then over 1 mole of barium hydroxide.
Good job. And now what do I do?
So now, since we are in moles of hydrochloric acid, you write the moles that's given, or the molarity that's given, which is, so on top you put 1 liter, and then at the bottom you put 0.3428 molarity of hydrochloric acid.
Good job. And then that's it. Once you get that answer, you convert it to milliliters, and it's the same that we did in the first problem. Good job. That's it. So hopefully you guys see this is not hard. We've done much worse. This is really easy. Again, what's hard is nomenclature. You guys have to get your nomenclature down. So tell me the time, please, because I don't have my...
58, but I had a question.
Okay, go ahead.
So on the exam, are they going to be written like this, or are you going to use the word form?
Words.
Okay.
I will always use words. I am never going to give you a formula unless that's not the purpose of the problem. The purpose of the problem is something else, and I don't want you to waste time on, you know what I mean? Like, but more than likely, you're going to get words. Barium hydroxide reacts with hydrochloric acid. So you need to know what that is. And then there's like 1 minute left, but I just want to read it. We don't have time to do it, but I want to read the last problem. I love this problem because it doesn't really tell you any information. You just have to, conceptually, you have to know what's going on. So during a titration, the following data were collected. A 10 ml portion of an unknown monoprotic acid. They don't even tell you what it is, right? So what does monoprotic mean?
1 proton?
So would it be something like H2SO4?
No, it'd be
a monoprotic? No, that would not be a monoprotic. That would be a diprotic acid. This is an example of monoprotic acid, but it doesn't matter who it is. They just tell you any monoprotic acid, right? So a 10 ml portion of an unknown monoprotic acid solution was titrated with 1 molar sodium hydroxide. Okay, 40 mils of the base were required to neutralize the sample. It's the same type of problem as before, but the only thing is like you don't know what the hell the acid is. Okay.
Do you just use X? Or how do you, when you're doing your problems, how do you represent?
Well, hold on, yeah, give me a second. So the question is, what is the molarity of the acid solution? Okay, so to find molarity, you need moles of the thing over liters of the thing, right? But you don't know who the thing is. The question I have for you guys is, and that you can think about is, does it matter? Do you understand what really determines everything in a titration problem? Like, what's the most important thing in a titration problem that you think?
Moles?
Yes, right. It is moles. That's why when people don't do reactions, it freaking pisses me off. Because like, how are you even getting an answer if you don't know the reaction? If you don't know the how it's balanced? And here's the thing: is that some students, and I've seen Jalen do this, I've seen Omari do this when they teach titrations. They use fractions. They don't even do a problem. They just write X, like you said, X over something, and then the other side has all the information. I don't like doing that. I like you actually writing down the equation and figuring out what ratio base to acid is, because that is the key of a titration problem, is knowing the ratio of the base to the acid. And if you realize what ratio is this last problem, what ratio would it be?
Okay. 1 to 1.
Why 1 to 1?
Because
for every acid, which has a proton, right? For every H plus, there's going to be how many OHs?
1.
That's right, because it's only NaOH only has 1 OH. So the ratio is 1 to 1. If you looked up here, the rate, how many protons from the acid are in protons of OH, in moles of OH?
2 to 2?
No, there's 1 mole of barium hydroxide. I understand, I see what you're saying about because there's 2 hydroxides there, but the compound is barium hydroxide. So there's 1 available OH for 2 available protons.
because of the mole to mole ratio. Right? You're looking at the coefficients. You're looking at the coefficients. That's what's most important in a titration problem. You can figure everything out if you know the mole to mole ratio of the base to acid. So if I'm reacting sulfuric acid with sodium hydroxide, that's going to be a 2-to-1. Why? Because sulfuric acid has H2 and what did I say? What did I say? Sodium hydroxide only has 1 OH. Right? Go ahead.
So when you looked at the other one on the bottom, the third example, you knew that it was a 1H plus because it's monoproctic. But when you're looking at, so say for the base, it was calcium hydroxide, and that was like CaOH2. Would it be 1 to 2 moles or no?
So do it. What's calcium hydroxide? Oh, hold on. I think we ran out of time, but oh my God, why isn't this letting me erase? Okay, hold on. Sorry. Do it. Do the problem. HCl plus calcium hydroxide. It would be calcium 2, right?
Yeah.
So the doesn't matter what the product is, but it would be water and calcium chloride, which would be calcium CaCl2. Balance it for me.
It would be
Dr. Tournay, am I excused? I have to.
Yeah, you can go. You can go. This is recorded, so yeah, you can go. I understand it's after class.
You have a blessed one.
Thank you. You too. Is that not balanced right there?
Wait, did you add 2 2s or 1?
I had 2 2s.
Yeah, it is 2.
So what is the molar ratio?
1 to 1.
What?
Are you looking?
Acid to base.
Oh, 2 to 1.
Right.
So wait, the calcium one wouldn't be the one with 2 though. It'd be the
Right. It would be the HCl because it's the coefficients. It's how many available protons versus how many available hydroxides there are. That doesn't, you don't like it. That's confusing you, isn't it?
Yeah, I'm kind of confused.
It's okay. So to not be confused, write down the titration, write down the reaction, and balance it. And that's it.
But even if they don't give you a...
But it doesn't matter because all you would do is give yourself an example of a monoprotic. So you would write HCl plus NaOH. And here, when you balance it, it's 1 to 1. And you'll see if you do NaCl, and I know I'm writing over stuff, but plus water, balance that equation now. Balance NaCl, this equation that I've written on top of other words. That is Na, ClCl, H2. So you would have
1 to 1.
Yep, exactly. It's 1 to 1.
So you can just give yourself an example.
Yes, that's the whole point. It doesn't matter because every monoprotic acid would be a 1
time.
Would be a 1-to-1 ratio with a mono basic base. I don't know if that's correct terminology.
So the the sodium hydroxide, that is, it's monoprotic because, or not monoprotic, but is it called monoprotic?
Mono basic?
Yeah, that, you would know it's that because just by looking at it, because of what? I guess that's like my main question. I guess that's where the confusion is coming in.
Because there's only one there to give, right? So there's only one OH. It can't produce any other OHs it has. So when you look at the other examples, right? For every 1 mole of the one on the top, for every 1 mole of barium hydroxide, there's 2 moles of hydrochloric acid. In the bottom, in this monoprotic example, for every 1 mole of sodium hydroxide, there's a 1 mole of hydrochloric acid. It's about balancing.
Is it because you need 2 OH?
Where?
Like for the second example?
You would,
Like,
what do you mean you need 2 OH?
like if you're looking at it, it's OH2 for when it's combined with the barium, but the first one is only 1H, so you need 2 for them to come together.
Of course.
Okay.
Yeah, I mean, because again, everything is about balancing, right? You don't just throw stuff away or make stuff up. So you've got to have enough of both to make water. And since there's for every 2 HCl's, there's only 1 available barium hydroxide that you can take, that you can use. And the opposite is true. Here, there's only for every 1 HCl, there's 1 OH. So I can make water with that. But okay, so Chloe, don't stress yourself out about knowing the ratio. The easy way to do it is write the reaction and balance it. That's it. If you write the reaction, and it doesn't matter what monoprotic acid you use, you could use HBr, you could use HCl, you can use, I don't know, HF, which HF is a weak acid, but you can use that, and it doesn't matter, because you're always, the ratio that when you balance it is going to be 1 to 1. So it doesn't matter what example you use, as long as if I gave you an example that says diprotic, then you would pick any diprotic acid and multiply or react it with whatever I'm telling you as far as the base, and get.
So an example of a diprotic acid would be like sulfuric acid.
Correct.
And then triprotic would be like carbonic acid.
No, carbonic is a diprotic acid.
Phosphoric acid.
Yeah, phosphoric acid.
Okay.
Yeah. Okay, and we're really, really late, so I'm sure we've lost a lot of people. So let me stop sharing. Thank you guys for staying. But you guys, so tomorrow we'll talk about this a little bit more, but we're gonna do dilutions, which are even easier. It's really easy. It's really easy. So all you got to remember is M1V1, and you don't have to remember it because it's on your sheet, but M1V1, M2V2. And then that's it. Then your exam on Friday, okay? Any questions, concerns? Okay, guys. Well, thank you. Thank you for staying.
Bye, Dr. T.
Bye, darling. See ya.